The next we are having the packing efficiency for the unit cell. Here we are talking about the mainly mainly about the simple about the cubic cell. And cubic cell we have, as we know that there are the three types of cubic cell, that is a simple body centered and face centered cubic cell. So here we are having we have to calculate the packing efficiency of simple cubic cell. Now what is packing efficiency? See, packing efficiency means we all know that the particles, the simple cubic cell or body centered or face centered, in all the cases the particles that is which are spherical in shape, they are arranged in a particular manner. And when the particles are arranged, like here the particles are arranged in some definite manner. Now in this case what happened, the some space is occupied, they have all the particles are arranged in a closed pack, means they are having a closed pack structure, means they are compactly packed, but still they are compactly packed, the some space is left in between. These are the space which is not occupied by the atoms. So determining the packing efficiency means trying to know that how much space is occupied by the atoms, that is the spheres, and how much space is a vacant. The vacant space are always in the form of void. So here packing efficiency means I wanted to know that if the particles are arranged in a simple cubic manner. Simple cubic packing means A type packing, three-dimensional. So when the particles are arranged in A three-dimensional A type packing, then how much space is occupied by the atom and how much space is vacant. So ultimately I have to just find out the same thing in fraction as well as in the percentage. So now let us see how to calculate the packing efficiency. I am talking about the simple cubic cell. So the simple cubic cell is the one where the particles are present on the corner only. So let's draw a simple cubic cell. So this we have the simple cubic cell where the particles are present on the corner. Okay. So I want to know the packing efficiency. Now in the case of the simple cubic cell, the particles which are present on the corner, they are always in a contact with each other. As I said, packing efficiency means I just wanted to know that how much space of an atom, how much space is occupied by the atom out of the total available space. So packing means for packing efficiency we have a formula. The formula is packing efficiency is equal to, it is volume occupied by the atom upon volume of a unit cell. And here the unit cell is nothing but the cubic cell, that is the volume of cube, I can say then. So volume occupied by the atom which is a spherical in shape, it may be atom, maybe molecule, it may be ion, depending upon which type of solid it is. We are just considering atom. So volume occupied by atom in a simple cubic cell, there is how many atoms? Then I can say that in simple cubic cell the particles are present only on corner, and the corner particles contribution is 1/8. There are 8 corner. So total number of atoms is equal to 1/8 into 8, that is 1. So volume occupied by one atom, and atom is a spherical in shape. So the volume of a sphere I can say is 4/3 pi r cube upon volume of unit cell. Volume of unit cell, that is here the cell is a cubic, that is a cube, and being a cube, the volume of a cube is a side cube, and here I am representing the side by a. So it is going to be 4/3 pi r cube upon a cube. So we got this relation for the simple cubic cell, 4/3 pi r cube upon side cube. Okay, now in the case of this, this is a, this length is a, that is a side of cube, this length a, this length, all the sides, since it is a cube, so if one side is one edge, the length of one side is a, that means all the sides will be equal to a only. Okay, so 4/3 pi r cube upon a cube. Now, if I want here the answer for the packing efficiency, and the answer can be calculated only if there is a R in the numerator as well as the R in denominator. Once I got R in denominator, then RR will get cancelled, and so that only the numbers will be left which can be solved easily. So I just want the relationship between the R and A, where R is a center of these spheres and A is a what? Edge length. Now here I know that these particles which are present in the case of simple cubic cell, in case of simple cubic cell, they are touching to each other. They are in a contact with each other. They touch to each other, right? That means if I'm considering this point as a A and this point as a B, that means center of this particle is A and the center of this particle is B. So here these two spheres are, they are like, this is A and this is point B, I'm just joining them. This is AB. And the length of this AB is how much is considered? It is considered as A centimeter or A picometer. Where I can say that these two, both the atoms or both the spheres are of same size. So this is the radius of this sphere and this is the radius of this sphere. So ultimately here this is nothing but the full diagram or actual diagram for these two, this side, where the side is a smaller one and the spheres are bigger in size. So here from this I can say that the A is equal to, we have a relation that is a 2R, and a very very important relation it is. A is equal to 2R for simple cubic cell. It's a very important relation. So for simple cubic cell we got a relation that is A is equal to 2R. Okay, after now we can substitute this value into the here. So we will get 4 by 3 pi r cube upon A cube. A cube is nothing but the 2R, I got a relation, so 2R cube. So we can say that it is 4 by 3 pi r cube upon 2R cube. 2 cube is 8 r cube. It is equal to r cube will get cancelled. So finally I will get 4 by 3 or I can say here 4 1s are 4, 4 2s are 6. So I can write pi upon 6 here. 3 will come. So pi by 6, which is equal to 0.524. This is packing efficiency in fraction form. Suppose if you wanted to write in percentage, then in percentage it can be written as multiply by this 100, 0.524 into 100 will give you 52.4%. So packing efficiency in percentage it is 52.4, in fraction it is 0.524. So this much packing efficiency for the simple cubic cell is 52.4. It means out of total available space, the simple cubic cell in a simple cubic cell the atoms occupy in 52.4% space and the remaining space is vacant. That means it is in the form of void. So here the void I can say it is equal to total space I will consider 100 minus 52.4%. That means you will get 47.6%. This is the vacant space I can say in the case of simple cubic cell. So simple cubic cell which contain one atom, and this one atom occupied out of total available space in a cube, out of total available space. Suppose this is the cube. Packing efficiency means what? Suppose this is the cube. And if I'm joining these corners, then I will get a one sphere. So if I'm keeping that one sphere inside the cube, then total space is equal to nothing but the space present in a cube, and I'm keeping that one sphere inside the cube. So that one sphere will occupy how much space is the packing efficiency. So if you are keeping that one ball or one sphere inside the cube, then that ball or sphere is occupying 52.4%. That means the remaining 47.6% is a vacant, and that vacancy is because of the voids which are present between these spheres, these voids. That means this much space is occupied by the void, or it is a vacant space. The next we are having a face-centered cubic cell. We have to calculate the packing efficiency of face-centered cubic cell. A face-centered cubic cell is the one where the particles are present, that is the atoms are present or spheres are present at the center, at the corners as well as at the center of each faces. So now let's see the face-centered cubic cell where the particles are present on the corner and at the face center. So this is the face centered cubic cell. The particles are present at the corner and at the center of each faces, side faces, upper and bottom. This is back face and then this is front face center. Okay, now here the particle which is present at the face center touches to all the corner particle of the same face. We have to calculate the packing efficiency here. So for calculating a packing efficiency, again I have a formula. That packing efficiency, the formula is same. It is equal to volume occupied by the atoms. How many atoms we have here? So I can say in case of FCC, we have total 4 particles. How 4 particles? 1 by 8 from each corner, that is 1 by 8 into 8, 3. 1 by 8 into 8, that is 1 from the corner, and half into 6 from the 3 faces. That means I can say 3 particles from the faces. So the total particle I can say 3 plus 1, that is a 4. So it will be a volume occupied by 4 particles of 4 spheres upon volume of unit cell. Again the unit cell here is face centered unit cell, cubic cell. So volume occupied by the 4 particles. The particles are spherical in shape, so it is going to be 4 by 3 pi r cube upon volume of a unit cell is a cube. Again I want the relation. Again if you want to solve it, then you have to find out the relationship between the A and R. So A again a edge length and R is a radius. So now let us calculate the relationship between A and R. Simply I will say that if you want to know the relationship between A and R, then you just find out a line in a unit cell which touches to so that whatever the particle falling on it touches to each other. Okay, before that, suppose I'm talking about in case of simple cubic cell. In case of simple cubic cell, at least the particle which was present on a corner was touching to each other. The particle present on a corner was touching to each other. Now, the question arises whether the particle present on a face center touches to each other or not. Sorry, particle present on the corner of corner in a face centered cubic cell, that is FCC, touches to each other or not. Suppose if I'm considering this face as a simple cubic cell, the face of a simple cubic cell. In case of simple cubic cell, how it was like 4 particles. And if I will join these corners, the centers, I will get the face. That means this area. But in case of face centered, what is happening? In between the face center, that means at the center of this face, there is a one more particle. At the center, that means a particle will be here. And the particle is going to be of the same size. And if the same size particle is, suppose if I am keeping the same size particle, what do you think that same size particle will fit into this void or not? Then answer is that the same size particle cannot fit in the void. So ultimately, but we are fitting it, that means so that what will happen, all the particle, when I'm keeping the 5th particle at the center, then other 4 particles will move slightly away from each other to provide the proper space for this 5th particle which is present at the face center. So now it will become something like this. So now this is the condition for the FCC cell. Now I can say that the particles which are present at this is the FCC. These are the centers. So I can say that in the case of face-centered cubic cell, like a simple cubic cell, the particle present in a corner particle present in the face center, they do not touches to each other. So if the particle present on a corner do not touches to each other, so at least I cannot say that A is equal to 2R. This relation is not true. A is not equal to 2R in this case. A is not equal to 2R. So finally we have to calculate, or we have to determine the relationship between the A and R. So to get the relationship between A and R, just find out a line so that whatever the particle falling on it touching to each other, or such a line so that whatever the particle falling on it touches to each other. So here I can say that the such line is this is the line. so that whatever the particle falling on it touching to each other, so we have three particle which is present on this line and all three particles touch each other. So now this line, same line here I can draw. In this case also this line is nothing but the diagonal of a face. I'm calling it this point as a, this point is a B, and this is point C. So AC is a line so that whatever particle falling on it touches to each other. So this is point A and this is point C. Now I can write the relationship between AC and R. Here I can say this is the radius. As I said, this is the center. So this is the radius. This is going to be a diameter, that means 2R, and this is going to be again radius. So I can say here AC is equal to, we got a relation that 4R. Question number 1. Now find out the AC is equal to, we have to finally calculate or determine the relationship between A and R, small a, that is the edge length, and the radius. So to get that relation, now find out that AC is equal to how many A. Now AC, this is point A, C, and this is point B, I can say. So AB is equal to here A, that is a edge length. BC is again a edge length, that is A. So if you want AC formula, then AC is equal to, I can say that here, I will use the Pythagoras theorem. The Pythagoras theorem, because this angle is going to be a 90 degree. This is 90 degree because it is an angle of a cube, and all the angles of a cube is a 90 degree. So by Pythagoras theorem, I can say that AC square is equal to, that is hypotenuse, is equal to AB square plus BC square. AB and BC both are A, that is A plus A, so I can say 2A square. This is AC square. So AC is equal to, I can say that root 2A. This is equation number 2. I got AC is equal to how much R and AC is equal to how much A. So from 1 and 2 I can relate A and R also, 2A. We can relate A and R. So from 1 and 2, root 2A is equal to 4R. So I can say that A is equal to 4R upon root 2, that is 2 root 2R. So finally we got a relation, A is equal to 2 root 2R. Again, a very important relation, and this relation is for FCC. For simple cubic cell, we have a relation between A and R as A is equal to 2R, but for FCC, we have relation A is equal to 2 root 2R. So let us substitute that relation. So here I will have 4 into 4 by 3 pi r cube, that is 16 upon 3 pi r cube upon 2 root 2 r whole cube. So it can be written as 16 upon 3 pi r cube upon 2 2s are 4 2s are 8, 8 into 2 root 2 r cube. This 8 2s are 16, 16 cancel. Then we will have r cube will also get cancelled. So pi upon 3 root 2. Okay. So it's a pi upon 3 root 2. Pi upon 3 root 2 on cancellation it will give you 74%. 0.74. So this is the fraction of the total space which is occupied by these atoms. That means this is the packing efficiency in fraction, that is 0.74. So if you want to convert it into percentage, then multiply by 100. So in percentage I can say that it is going to be 74%. That means out of total available space, the 74% space is occupied by the atoms or the particles in the case of FCC cubic cell, that is FCC unit cell. And the vacant space, that is a void, will be equal to 100 minus 74, that means I can say 26%, or in fraction I can say 0.26. So packing efficiency of face-centered cubic cell is more than the packing efficiency of simple cubic cell. For simple cubic cell, the packing efficiency was only 52.4%, while for this we have 74%. The value is very high compared to simple cubic. That means compared to simple cubic cell, FCC is a highly packed structure. That means the packing is a very strong or efficient in the case of FCC unit cell. So in FCC unit cell, we got the two things which is very important, that A is equal to, I got 2 root 2R. And here I can say void, the space occupied by the atom is equal to 74%. The next we have to calculate the packing efficiency for the body centered cubic cell, that is I can say the BCC cell. So here we have to calculate the packing efficiency for BCC cell. BCC cell where the particles are present at the corner, as well as there is a one particle which is present exactly at the center of the body. So overall I can say that there is a two particles or the two atoms which is present in a body centered cubic cell. So we have to calculate packing efficiency, means ultimately I just wanted to know that how much space is occupied by these two particles in a unit cell. So now let's see the body centered cubic cell. So this is the BCC cell where the particles are present on the corner as well as at the center of the body. We have to calculate the packing efficiency. The packing efficiency formula is same, that is volume occupied by, in BCC we have two particle, the two particle that is 1 by 8 from 8 corners, so we get one particle from the corner, and there is a one particle which is present exactly at the center, and the particle present at the center is not shared by the other unit cell, so it's a totally present in the same unit cell, so one from the corner and one from the body center. So the volume occupied by two atoms which are spherical in shape upon the volume of unit cell. Volume of unit cell. Volume occupied by two atoms, it's a 2 into 4 by 3. The sphere atoms are spherical in shape, so the volume of sphere upon volume of a unit cell is again side cube. So again, if I want the packing efficiency for a body centered cubic cell, then first I require the relationship between the A and R. So let us calculate the relationship between A and R for BCC. Now in case of BCC, I can say the particles which are present at the center do not touches to each other, but the particle which is present at the body center touches to all the particles which are present on the corners. So the corner particle do not touches each other because of the presence of this particle exactly at the center of the body. But as I said, the particle present at the body center touches to all corner particles. Now here again, if I wanted to know the relationship between the A and R, so first we have to find out a line, so that whatever the line says that whatever the particle falling on it touches to each other. So I have to draw a line in a diagram so that whatever particle falling on it touching to each other. So I can say that if you want such a line, then simply draw a body diagonal. The body diagonal, that is the diagonal of a full unit cell, a full cube. So I'm just drawing a body diagonal in this case. The front corner of the cube will touch to the body center particle and is directly touching to the means this line is drawn from the front upper corner of the cube to the lower corner of the back face. So this particle is directly in contact with this particle as well as this particle. So here I can say that this is point A and this is point D. So I got AD. So here I can write that AD is equal to 4R, and AD is a line so that whatever particle falling on it touches to each other. Equation number 1, AD is equal to 4R. Okay, now here I have this AC, this DC length is A, then I'm just drawing this AC also. AC is how much? In last derivation, that is in while determining the packing efficiency for the simple face centered cubic cell, we got the relationship, we got AC also, and AC was nothing but root 2A. So I have AC is equal to root 2A, CD is equal to A, and finally I want AD. I got AD is equal to 4R. How 4R? Because it's the diameter of this and radius of this and radius of this. Diameter, that is 2R, radius of this 3R, and the radius of this, that is a 4R. And then now I just want the AD is equal to how much A. Once I got the relationship between A and R, I will get the packing efficiency also. So to get AD is equal to how much A, let us calculate the value of AD in terms of A. So here I am considering first how I got AC. So for AC, I will use this formula. AC square is equal to AB square plus BC square. AB and BC both are the sides of a cube, so A square plus A square. So I can say that AC square is equal to 2A square. So AC square is AC is equal to, I can write that root 2A. So I got AC. Once I got AC, we have to calculate AD now. So for AD, I can draw the diagrams like this. There is a one particle, this is point A, present on this. There is another particle present here, and there is a one more particle present here. This is point D, and this is C. So finally AC is equal to, I know that it is root 2A, we just determine. CD is A, and I have to calculate this AD. AD is equal to, I can say this is a radius, this is diameter 2R, and this is R. That's why AD is equal to 4R. Now I want AD is equal to how much A? This is again 90 degrees, so again I can say use Pythagoras theorem. So by Pythagoras theorem, I can say that hypotenuse square, AD square is equal to AC square plus CD square. So AC square is root 2A square, that is 2A square, plus CD square is A square. So I can say that it is equal to 3A square. AD square equal to 3A square. So AD is equal to, we can say that it is root 3A. This is equation number 2. From 1 and 2 now I can say, from 1 and 2 I can say that root 3A is equal to 4R. So A is equal to 4R upon root 3. So this is the relation which we got between A and R, that A is equal to 4R upon root 3. So this is the relation which we are having. Now, once I got the relationship between A and R, let us substitute this relation in the packing efficiency so that I will get the value for packing efficiency also. So the packing efficiency is a 2 into 4, that is 8 by 3 pi R cube upon A cube. A cube is 4R upon root 3 whole cube. So here I can say that 8 pi R cube upon 3 upon 4 4s are 16 4s are 64 R cube upon 3 root 3. This 3 will get cancelled, 8 8s are 64 R cube will get cancelled. So here from the numerator we have pi, root 3 will move to the numerator, so pi into root 3 upon, in denominator only 8 is left. Okay, so finally on substitute all the values and solve it. After solving, you will get a value that is 0.68. So this is the packing efficiency fraction of packing efficiency. If you want to convert it into percentage, then I will say multiply by 100. So after multiplication, I will get 68%. That means out of total available space, I can say that 68% space is occupied by the atom and the remaining spaces are left. The remaining spaces are left, that means it is nothing but in the form of void. So vacant space is 100 minus 68, that means it is equal to 32%. So this is the packing efficiency for the body-centered cubic cell. The body-centered cubic cell, I can say its packing efficiency is less than FCC. See, I can say for the simple cubic cell, for simple the packing efficiency is 52.4%. That means the least packed packing. And I can say, I simply remember that simple unit cell contain only one particle, and that's why its packing efficiency is less. BCC, it occupies more than simple, that is 68%, and this is possible because here we have two particles. FCC contain the highest number of particles in a unit cell, that is 4, and hence its packing efficiency is also highest, that is 74%. So simple cubic cell packing efficiency is the least, then BCC, and then in FCC the packing efficiency is the highest one, that is 74%. For packing, for the relationship between A and R, I can say for simple we have A is equal to 2R. For body centered we have A is equal to A is equal to 4R upon root 3, while for the FCC we have a relation A is equal to 2 root 2R. So this is about the packing efficiency of the body centered cubic cell.